Thank you, Tarek. That was it's quite a hype man. Rockstar, I don't know about that, but okay. Anyway, so right, so I'll be telling you tonight about Coda. Coda, you might wonder, what is that? Well, let's find out. Oh, sorry. Before I go any further, if you has anyone seen me give this talk in some form or another before? Okay, I don't want to disappoint these people who've already seen it. I'll try and make things a little bit more interesting or new or something, but for the most of you, it's new, so that's good. Okay, so yeah, what is Coda? So Coda is a new cryptocurrency protocol. It's the first cryptocurrency that has what we call a succinct blockchain. And what is a succinct blockchain? Well, it's a blockchain which is small and easy to verify. So in particular, for Coda, the whole blockchain is essentially this, just about a kilobyte, regardless of how many transactions happen or basically how many people are using it. So what's the cool thing about this? It makes it possible to have a blockchain which is scalable while still being secure and having very decentralized verification. In particular, the verification is so cheap that you can do it even on a mobile phone. You download this little proof, it's a kilobyte, and you check it in about 10 milliseconds-ish. And that's just as good as if you were running a full node, and you can do that on a phone, or even in a web browser, as we'll see. So let's talk about cryptocurrency for a moment. This is the usual setup of cryptocurrency, well, as rendered by me. You have here a database, okay? And you have some people who are managing the database, who are modifying the database, or maybe even just looking at the database. Who are these people? Well, they're either miners or they're full nodes. So people who are either adding transactions or modifying this database, or who are aware of this database and aware of its history. And then on the other hand, you have people who are end users who are typically themselves not full nodes or not miners. And they're sort of delegating trust to these people who are interacting directly with the database. Right. Okay, so let me say it in a little bit more structured way. What I'll call transaction processors, these could be miners, these could be stakers. They apply transactions to this database. Full nodes are watching. That's like this. Say this person over here is a full node. Okay. They're not so greedy, not so evil. They're maybe just a person. They're just kind of watching what's going on, and they can really see if the processors are doing the right thing. But at the end of the day, you have these end users, the majority of which just delegate trust to either the processors or the full nodes, while they themselves do no checking. So this isn't a great state of affairs because, as you can see, the processors are they're usually either greedy or maybe even evil. So it raises the question: what's the deal? Why can't everyone be a full node? Well, probably most of you know, but let's see why. So how does it usually go for a full node? Okay, well, on day one, it's a genesis block. You're happy. It's a very small blockchain. You check the whole thing. It's very good. But what happens is you wait a second, and the blockchain grows, right? It's a chain of blocks. Okay, what did you expect? So you wake up one day. It's super long. You're like, oh crap. What am I going to do? Well, I guess I'll have to verify this. I am a full node after all. And you go and you go and you go, and at the end you're there, and at the end you're very old. And I guess you verified the blockchain, but I don't know. Was it worth it? Probably not. So that's why most people are not full nodes, right? The resource requirements are very large, and they only get worse over time. So as anyone who's tried to run a full node on a computer can attest, it's such a pain in the butt to run on your computer, and it's completely out of reach for running on a mobile phone. And so what do? You delegate trust to third parties. So either a full node, that's like in the case of like an online wallet, a Coinbase, something like that, or maybe to miners in the case of Litecoins. So how do we get around this? Well, what we need is some way to be convinced of the current state without seeing the history of that state. Okay, does it make sense? Yeah. Right? Makes sense? Who thinks it makes sense? Okay. Great. Right, so the root of this problem is just how the verification mechanism works in a typical cryptocurrency. How does it work? Who knows how it works? Probably most people here. Yeah? Huh? You look at the history, right? So you want to know, someone sends you some money, you want to know, does this person have this money? What do? You look at the history, right? It's like every time someone tried to send you a dollar, you had to check the entire history of that dollar. So, someone tries to pay you, you say, oh yes, well, they got it from their job as a cashier, and well, yeah, the customer got it, I don't know, from returning something at the store, and well, that person got it, from their boss, and they got it from, I don't know, I'm not sure who this is. Huh? Who is it? What's it? Okay, I'm not sure. They got it from I don't know, somehow, and that person got it because they are the manager of a fast food store, and so on and so on. You don't want to know that. That makes no sense. It really doesn't. I mean, when you tell, I don't know if anyone else has had this experience of explaining to someone how cryptocurrency works, and they say like, that makes no sense. And really, it makes no sense. Why should you have to see the entire history? Well, okay, so let's think about a solution. Well, what we would like is some way of certifying that someone else had already checked this state for us. Okay, like some kind of certificate. But you could think of it as an analogy. Maybe you wanted to invest in a business, but you don't want to look through their whole financial history yourself. What do? Maybe you get an auditor to do it for you and produce some kind of audited financial statement. And this is a much easier thing to check than checking their finances yourself. Okay, this isn't really a perfect analogy because what's wrong with this? Well, this is sort of like delegating trust really to someone else and having them check it for you. So we don't want to do that. But it turns out there's this amazing thing which is called a zk-SNARK, and this is a kind of unforgeable certificate. So it's a certificate that requires no real delegation of trust. As I said, it's an amazing cryptographic primitive, and what they are is basically a certificate to prove that you ran some computation correctly. Okay? So the cool thing about them, there are three cool things. One is that they're tiny. Okay, so they're actually less than a kilobyte. They're very easy to check, as I said, just a few milliseconds. And they're very versatile. So you can use them to certify any computation that you like. They're a universal technique. And please note, SNARKs are tiny and easy to check, regardless of how complicated the computation was. So to give you a sense of things, this could be a computation that took 1,000 years to perform, 1,000 years. And at the end, you could produce this certificate to be assured of the result of the computation, even though you haven't been around for 1,000 years, you have no idea what kind of hardware the computer was running on, et cetera, et cetera, et cetera. You would still have some confidence that the computation was run correctly. Now, maybe 1,000 years, maybe that's really a bit far-fetched because probably quantum computers, et cetera, et cetera, et cetera. So who knows, but this gives you a sense of what I'm talking about here. It's tiny and easy to check regardless of how long the computation takes. So how can this be used in Coda? Well, updating a blockchain, those things that those evil gray people were doing, that's just a computation, right? Those are programs. SNARKs, as I just said, if you believe me, can certify any computation. So what could we do? Well, we could have processors produce SNARKs which certify that they're actually updating the blockchain correctly. So they're really checking the signatures, they're really checking the account balance, they're really subtracting the account balance correctly, the nonce, et cetera, et cetera, et cetera. And then, instead of end users checking the blockchain themselves, well, they can just check the certificate, okay? Make sense? Why not? And remember, the certificate is tiny and easy to check. So instead of having to download the super long blockchain, they just download this 1 kilobyte thing and they check in 10 milliseconds, and you're good to go. So what does it mean? It means you get basically a full node level of security while only downloading a few kilobytes, okay? So let's investigate a little bit more. What exactly is the SNARK architecture, as we say? what would be one attempt is to use just one SNARK for each block. So you have the processor, and they produce a SNARK while updating the database of accounts. Okay? This processor is thinking about something. Maybe you could guess what it is. Okay, so this is the completed certificate. What does it say? It says the database of accounts started in state 1. I did some stuff, and I did it correctly. And then at the end, it was in state 2. Okay? So as I said, it says basically, I know a block, which when correctly applied to database 1 results in database 2. Okay, so that's what this certificate says. It's a proof of that fact. Or simply, just for ease of language, so I don't have to keep saying a long sentence, you can get from DB1 to DB2. That's how I'll say it, because I'll be saying that a lot, so I just want to say it like that. It's a SNARK, so this is just a kilobyte. OK, so what happens for the end user in this world? Well, the end user checks the certificate saying you can get from DB1 to DB2. And actually, this is DB1. Who knows what it's a Merkle tree? OK, so basically, this DB1 is really the Merkle root of the whole database of accounts. OK, and so they also get, in addition to the certificate, they get a Merkle path into that database 2 to get their account balance. And it says you have 17 Codas, and that's how they check their balance. Well, OK, so that's cool. They can be assured of their balance without having to see the diff between database 1 and database 2. Which would be fine if they already believed that database 1 was the kind of current state of things. But what if they didn't know that database 1 was the previous state, in a sense? You with me? Do people see what I mean? Well, OK. Well, you can kind of imagine that you can chain these certificates together. So, if you have, let's say, the Genesis database of accounts is database 0, right? So you have one certificate that says you can get from DB0 to DB1. You have one that says you can get from DB1 to DB2. You have another that says you can get from DB2 to DB3. You have one that says you can get from DB3 to DB4, and they all check out. Well, you can, then you can know that, in fact, you can get from DB0 to DB4, right? Right. So it's almost like a blockchain, but instead of including the transactions or whatever in the blocks, you just use a sequence of SNARKs. And this would be a big win if the sequence of SNARKs was smaller than the sequence of blocks. Yeah, what's up?
So is that like just getting the header chain of the whole block?
Getting the
headers of the whole blockchain?
It would be as if you were just getting the headers, but also really checking the validity of all the transactions without having to see them. OK? So, but this doesn't solve the problem of linear growth, right? So the blockchain is still growing linearly with time. Eventually, even if these SNARKs are small, you'll still be under a pile of them. So attempt 2, this is what Coda actually does, is to use one SNARK for the whole blockchain. OK, well, how are you going to do that? Well, this is a really crazy idea. It goes back to, I think the first instance is this paper of Valiant. It's 2008 or something like that. It was his PhD thesis. It's pretty cool. I would read it. It's funny. He has this 1,000-year computation example in the introduction. This is the idea of recursive composition. So checking a SNARK, well, OK, that's computation, right? And what did we say? SNARKs can certify any computation. So the checking of a SNARK can itself be certified with a SNARK. Does that make sense? If I tell you, oh, I checked all these SNARKs and they were all good, I could get one big SNARK that kind of certifies all of that whole checking process. So what it means is that we can chain multiple SNARKs together to get one SNARK that stands in for all of them. Cool? So let's see a little bit more, I would say in detail, but it will just be with pictures. Let's see with pictures. So we have this one SNARK. It says you can get from DB1 to DB2. We run our SNARK checker. It says thumbs up. We have this other one. It says you can get from DB1 to DB2. Oh, sorry, did I say that before? I meant you can get from 0 to 1. We have this other one that says you can get from 1 to 2. We also run our checker on that. It says, yep, that looks good to me. So we can SNARKify this whole checking of both of them, right? And we get this one SNARK that says, yeah, I know a SNARK that says you can get from 0 to some intermediate state. And I know another SNARK that says you can get from that other intermediate state to state 2. OK? And they both verify. So you get one SNARK that stands in for both of these. And it's a SNARK, so it's still a kilobyte, and it still takes 10 milliseconds to check. So now, what are we going to do? We're going to do it again. We have one that says you can get from db0 to 2 now. We did it again, let's say. Now we have one that says you can get from db2 to db4. Again, we check both of these, thumbs up, and then we snarkify that whole situation again. OK? So now we have, again, just one snark that says you can get from 0 to 4. And it's standing in for the computation of, basically, I saw a snark that got from 0 to 2, and that one saw a snark that goes from 0 to some intermediate state. And, you see what I mean? So, yeah, it's like I know 2 people, they check 2 people, they check 2 people, and so on. Does it make sense? It's kind of funny when you think about it that way, I think. Like, it kind of also makes sense, right? Like, oh, there were 2 people, and I checked them, and they checked 2 people, and so on. I mean, I guess that's, I said it last time, but it's true. That's, I guess, how large organizations work, and even, in a sense, even societies in general. I mean, how many people do you talk to, right? What's up?
So what else is stored in that whole SNARK of 0 to 4? It's a proof, but what other things?
That's it. It's all it says is there was a bundle of blocks that got you from state 0 to state 4. Because all you really, you don't necessarily care about the history, right? You just care, what is my current balance, and well, some other information perhaps as well for consensus and for checking which transactions were sent and so on. But there are sort of, those are sort of details that. Sorry?
You can't check the individual ones.
There's no, yes, in a sense, the SNARK is sort of maximally uncompressible because it's a zero knowledge proof. So there's really no way to reverse the process. You get no information besides the fact that there is some sequence of transactions going from 0 to 4. So OK, so let's break it down. What does the end user do in Coda? They download this basically 1 kilobyte blockchain snark that says, you can reach state 4 from the genesis state. And again, they get this Merkle path. I said 20 kilobytes. I should have updated these slides. It's actually like 2 kilobytes. I don't know why I thought it was 20. It's not a big deal, obviously, but they get a 22-ish kilobyte Merkle path to get their account info. Oops. And yeah, that's it. They check the Merkle path. They check the snark. That's like checking the whole blockchain, and you're happy. And you go and you spend your 17 Codas. So what's the upshot? As I kind of just mentioned, the Coda wallet, you can sync basically instantly to a full node level of security with just a very small amount of data. From a scalability standpoint, this is a huge win because often people talk about scalability, they talk about increasing throughput. But of course, this only makes verification more impossible. If you imagine thousands of transactions per second, it's like terabytes of data every week. Is that right? Yeah, terabytes of data every week that you need to verify if you actually want to check the blockchain. Most people can't keep up with that torrent of data, and this delegation problem, just grows. So, let me end by chatting a bit about what our progress has been as an organization, as a project. We started about 18 months ago. Since then, there's obviously been a lot of activity. In March of this year, we released Snarky, which if people are interested in zero-knowledge proofs, programming with zero-knowledge proofs, I really recommend that you check out. It's a programming language implemented as a DSL and OCaml for working with zero-knowledge proofs. I think, I've used the alternative things. I think it's better. I also wrote it, but so if you want to work with zk-SNARKs, I think it's a really good way to do so. And if you really seriously want to do something, I actually encourage you to contact me, and I can even help you. Let's see. Then in April, we released our white paper. In June, we grew our full-time engineering team to about seven people. Now I think we're 10 engineering and maybe 4 other roles. And September, we released our first test network. October, we open sourced all of our code, which brings me to what's going on now. We're shooting for Q1 of 2019 to have a feature-complete test network running. We'll be growing our development and product teams further, and there will be a bunch of ongoing efforts as we enter like the final testing period before main network. So we'll have bug bounty programs, security audits. We're developing a wallet and other applications on top of Coda. There's a bunch of ways to get involved. As I mentioned, we do all of our development in the open on GitHub. It's fun. You can come comment on issues and talk about crypto and stuff. You can chat. We do also all our chat on the open in Discord. You can join the development chat if you're into obscure things that are happening in our code base and chatting about OCaml and stuff. And follow us on Twitter. So I know I probably raced through that. What's the time? Oh, yeah. Oh, yes. 1 second. So, oh yeah, I guess we're doing questions now. So, okay, cool. I guess I'm done. Do other people have questions? I just, before I answer your question, I want to get a sense of how many questions there are. Okay, I'm going to choose randomly. Will someone say a number? 5. Okay. Okay, it's a good enough number. Yeah, you.
Can you talk about consensus a little bit?
Oh yes. So in what sense? So we use a proof of stake variant of Ouroboros. Just as checking transactions is a computation, checking the consensus rules is also computation. There's only a very small amount of state which is needed for consensus. It's something like, Ouroboros is very complicated. So if you say something like proof of work is basically how much work is in this chain, and what was the last timestamp, and what's the difficulty, right? So you certify that you're updating all of that information correctly as well with a SNARK. Does it make sense? Ouroboros is more complicated, but.
A follow-up question that's related to SNARK, I guess. I noticed that it hasn't been updated in a while, and
Oh.
number.
Oh no. Oh.
Also a version in the Coda protocol we have.
Oh yeah.
One we should be using.
Oh yes. Wow. Okay, that's so embarrassing. I will copy it out of there into the Snarky repo. I'm sorry. Thank you for letting me know. That one's up to date, and it's definitely there's a lot that happened since I guess. Yeah. Oh, 1 second. What's
So, did you do some statistics on actually changing the headers and changing transaction and then saying now you have stale data in terms of the SNARK? So, how long does that take? Right? So, the transaction changes. You have a SNARK. Now you have to go through the whole blockchain. Where do you get that computation about? Because you're saying it's sitting somewhere in the wallet, right? So you've got the signature there. Someone changes in the blockchain, it changes. Now that signature is stale.
I'm not sure I understand. Does anyone?
You have a chain
Oh, yeah.
of blocks.
Yeah.
And the transactions change after you get your SNARK. So
How do you mean?
the clock is not matched.
How do you mean it changes?
No, I'm asking what is the time difference between when you actually get the timestamp from the SNARK to when you say, because it's stale, right? Or maybe I'm missing something.
Can anyone interpret? I'm sorry.
Okay. So you've got a blockchain that's got each block has transactions in it, right? You get the zk-SNARK that matches the state.
You're saying for your transaction?
Yeah, so the transaction changes.
Yeah, so
Oh. You're saying when someone adds a block to the blockchain.
Yes.
Okay. Right. So right. So someone sends me a transaction. I'm waiting for them to. I'm waiting for that transaction to get included in the blockchain.
Right, the SNARK before is stale.
Yeah. Right. So the cool thing is the recursive composition makes it possible to incrementally update the old SNARK. So there was a SNARK that said you could get to the last previous state, and then you can add a new block on top of that and include it into the previous
And that's
SNARK.
coming from Ouroboros,
So
who's doing it?
who's responsible for producing that SNARK? It's the block proposer, so the staker. So basically, you win a block, you're responsible, in addition to telling everyone what the new transactions you're including are, producing the new proof that certifies the current state. Questions? Yeah.
So you use SNARKs, this implies you have a trusted setup, right?
Mm-hmm.
Why should I trust you, and why is it possible to use SNARKs instead?
I guess I would say yeah, I wouldn't, maybe you shouldn't trust me. I mean, I think I'm a trustworthy person, but yes, I don't know you. So, you know, at this point, the Zcash team has done really an amazing job of making it possible to run a really scalable setup. With, you know, the sapling setup, they had, I think, 70 or so participants. At which point, I mean, I don't know. For me, it's hard to believe that all of those people who are all running the software in all really crazy, you know, upside down in a airplane kind of ways, that all of them would be compromised and colluding. So at that point, to me, the trusted setup becomes not so much a security issue as just like a logistical issue.
Is it theoretically possible to use to generate like this scheme of SNARKs and SNARKs and using SNARKs instead?
It might be possible. There are technical reasons for which recursive composition is particularly efficient for SNARKs. It would be a sort of a research problem. Yeah.
If I understand correctly, that a full node in Coda would still need linear memory to remember all the balances?
Yeah, so linear in the number of accounts.
Yeah.
Yeah, that's right. Yeah.
Okay, so could you go back a slide?
Sure, yeah.
You had one, I just wanted to be clear, like for the mobile plotly. So in that case, what is the mobile downloads the top block and then Merkle pass to the account, right?
Yeah, that's basically right.
What does it actually verify to make sure that is in the right state?
So you download this proof. What this proof says is there exists a blockchain such that you know, if you take that blockchain, run through it, check all the transactions, aggregate all of the transactions together, you'll get a database of accounts with Merkle root, you know, 4, and that's what it says.
But it could be any blockchain, actually. This stuff knows, you know, can you create a fake block basically somehow?
So,
Is it possible?
well, you know, you do it the same way that if there are multiple, if people are telling you about multiple blockchains, you do it as you always do. You pick, well, basically the longest or strongest sort of chain. So there's a chain selection rule in the case of some ambiguity.
Well, like a mobile wallet usually doesn't do that.
But the SNARK does it. The SNARK is saying basically there is a blockchain. You know, let me say it in the case of Proofofwork because it's sort of simpler to talk about. There is a blockchain. You know, after seeing it, you would be convinced that the total you know, hash power in that chain, the total strength of that chain was S, and the database of accounts after seeing all the transactions in that chain had Merkle root H. And so you see, if you see two chains, two proofs, this one has you know, strength 100, this one has strength 105, you go with this one. And this proof is sort of a compressed version of having seen the entire chain in a sense. It's not really compression in the sense that it's irreversible, but it's sort of as good as compression because all you were going to do was look at it, check it anyway, and just figure out what the strength was and what the account balances were.
So I think you've almost answered it, but I'll let you answer this question. How do you guys compare to the global?
Yeah, so maybe I was chatting with someone earlier about that. So I think there are basically two major differences. One is the Mimblewimble technique is basically like it's kind of like that attempt number 1 that I showed. So it's like a linear reduction in the amount of, a constant factor reduction in the amount of space required. It still grows linearly with time. So that's one difference from Coda. Coda is, you know, just always 1 kilobyte. And the other difference is Mimblewimble is very particular to payments. So it's not a technique that you could generalize to more general kinds of computation, smart contracts, that sort of thing. Coda, you know, right now we've only implemented the payments version of the protocol, but we are planning on adding more general smart contract or computational functionality as we move forward.
When does it take to create one of these proofs for each one?
Oh, a long time. So yeah, let me say this, it's a long time. The cost of producing one of the proofs is sort of baked in a sense, the transaction fee. The number of proofs that you need to create is proportional to the number of transactions. If it costs some amount to make a proof, you charge that much in the fee. As you saw with the kind of tree structure, you can do all these proofs in parallel. So the total time for snarking 2 to the n transactions is logarithmic in n.
Just curious where your block time would end up.
So yeah, so it's a bit funny. The exact way that it works, it's possible to have a short block time regardless of how long it takes to do one of these snarks. There's some kind of buffering sort of thing that you can do. It'll probably be around 30 seconds-ish. Hopefully. Maybe shorter. Well, yeah, you have to use these really special, really crappy curves to do the efficient recursive composition. But yeah. What's up?
Okay, so if you spent that green amount there, does that get replaced like by no value or something?
So yeah, so the way that it works is Coda is like account-based. So if you spend some money, like 6 Codas or whatever, then the next time your account would be modified and the Merkle root would be the Merkle root of the tree, but with your account being replaced by the account that had 11 instead of 17. What's up?
Sorry if you've already gone over this, but is there a distinction between a full node and a non-full node? Did the full node store the UTXO?
Yeah, we haven't, I think, worked out exactly what the nomenclature should be, because it's a little different from your usual setup. But I guess usually I think about the nodes who are keeping track of the entire state, and the nodes who are just looking at proofs. The nodes who are keeping track of the entire state, that's probably going to be, well, either someone who has some pressing reason to do so, maybe an exchange or something like that, or someone who's a block proposer, so like a staker. If you're just someone who's interested in looking at parts of the state, there's no need for you to keep the entire set of balances. Does it make sense?
Yeah, I guess I was wondering how when you do go to verify your account, you have this Merkle path, but path into what? Like somebody has to store that.
Yes. So the people who are proposing blocks are storing the entire state.
Right. So when you go to check your account, I guess there's some hash of the whole thing, and then you can verify this path efficiently without having to get the whole UTXO set.
Yep. Yeah. So you have this proof which says there is a block. It's actually account-based. It's not UTXO, but you could do it with UTXO too. Basically, you would say there is a. Let's talk about UTXO if you like. There is a blockchain, of such and such a length, such that if you had seen all the transactions in that chain, you would believe that the UTXO set has Merkle root H, and then you just get a Merkle path into H. Okay. You've been waiting a little longer, yeah.
Can you comment a little bit on why your team chose proof of stake versus proof of work?
Oh, sure, I'd love to. Look, global warming is the most, one of the scariest and most pressing problems of our time, and to throw more coal on the fire to me at this point would be morally reprehensible. I don't know. Actually, it turns out as a side effect that that's also true. So
If you don't have Bitcoin's hash,
it seems very likely that for coins which are not the biggest proof of work coin, proof of work is probably not a very secure option. You'll get killed by something with more hash power, unless you do some obscure hash function that's only good on CPU. But even then, I mean, there's another CPU coin that's better than you, and so. What's up?
I think I'm a little bit confused how the whole schema works.
Okay.
I tried to explain how it works, I couldn't just say I'm correct or not. So where is the block proposers? So there are some like dedicated computers, whatever systems, which has enough memory and enough space to have copy of all account set.
Exactly.
And when someone's and let's say there's a wallet, and also wallet has like this dedicated machine. Like I make a transaction, I send like to you some kind of like a coin, and I calculate, well, I basically sign this transaction and I send it to a full node. And this full node calculate a SNARK of SNARKs and basically update the rule, right? And after that I can ask this, like later, let's say full node and ask for you to say like, how much money do I have in my account and generate me this market file, and I can verify. But how I can understand, like, so it's a different set of machines which keeps only like kind of your SNARK. So is it only full nodes going to give me this like short SNARKs which I cannot trust what is indeed the most recent SNARK and I can verify what market file belongs to it, or there is a more broader set among full consensus with reading what is the current SNARK. How do we call this current SNARK? Like blockchain SNARK?
Blockchain SNARK, yeah.
So, what is it? Who decides what is the most recent version of blockchain SNARK?
The stakers, so people who are
Full nodes.
full nodes or slash like block proposers, really. Yeah.
But full nodes and block proposers. Okay, so full nodes and block proposers
Really, yeah.
keep the whole transaction history or like at least accounts.
Accounts, yeah.
So regardless.
Yep.
So benefits is only to verify the transaction had happened for mobile wallets.
Well, for anyone who doesn't want to keep the entire state.
But you don't keep entire states. So in Bitcoin you keep like only headers.
Or yeah, right.
Which is like 32 megabytes.
Right. So if you're
You also have to download the whole history there.
if you're just keeping headers, that's sort of delegating trust to the miners, right? So if you're just keeping headers, the miners are writing, here's what the UTXO said is commitment, and then you get your Merkle path into that. But I mean, they can put whatever they want there, right?
No, like supposedly, how can I verify what the most recent?
Maybe we should have this. I don't want to. Maybe we should have this conversation after.
No, I think it's a really interesting conversation which goes to the root of maybe everybody's kind of, trying to understand where is the kind of, benefit. And it really sounds like we still have two classes of citizens, privileged citizens who have enough, compute power and can store the entire history, and clients who do benefit because they have this, recursive SNARKs and it's very easy, etc. But the benefits are only on the client side, right?
That's right. Yeah.
Right. So I'm not quite kind of, comfortable with having two classes of citizens again. Is it possible actually not to keep the history and keep only SNARKs? Somehow and still being able to propose a new block?
So it's actually it's interesting. There is actually some kind of impossibility result about cryptographic accumulators. I can't remember what paper it's in. I can ask someone and let you know, which somehow says actually you can't get that.
You cannot.
So it turns out either you need to have an amount of state which is sort of growing linearly with time, or you need to sort of constantly be online and constantly be getting updates and sort of updating your local state. Yeah.
But it is better for also sort of like the people, the consensus nodes, because in Bitcoin you have to, if you want to be fully verified, you have to download the entire blockchain, including the history that's no longer relevant to the current state. So the longer that goes on, the bigger that crowd is working.
Yeah,
So,
it depends on what you're comparing to. So because there are other systems where you have only one class of systems, for example.
Okay.
Can you please go just a couple of slides back and repeat how you do this recursion, if we have a few?
Sure. So maybe would this be, were you thinking here or in this case?
Yeah, from the beginning of how you explain the recursion.
All right. So you have this one proof which says you can get from state 0 to state 1. Another which says you can get from state 1 to state 2. Yeah.
Is it one transaction or is it whole block of transactions?
It could be either. Right now, it's just one transaction in the implementation, I can tell you.
Okay.
So,
So kind of, okay, one goes from 0 to 1 and another goes from 1 to 2, okay. Yeah.
yep. And both these SNARKs verify. You can run the verification algorithm and they both return true. Well, you can summarize that whole state of affairs with another SNARK, which says, I know 2 SNARKs, each of which verify. This one says you can get from 0 to some intermediate state, and this one says you can get from that same intermediate state to 2. Does it make sense? Should I say more?
No?
Oh, okay, okay.
It means like every change of states will inevitably change of a blockchain SNARK. You have to change a whole blockchain SNARK for every transaction, so it will collect all the very quick of the amount of transactions every time.
Right. So the way that the architecture actually works, there's sort of you sort of delay the inclusion into the ultimate blockchain SNARK for some time, but yeah. Anyway, it's maybe a bit out of scope for this talk.
There's another talk online that describes exactly how it works.
Okay.
You have it online, right? This presentation.
Yes, yes. Yeah, if you go on our website, if you go to codaprotocol.com, you can see the version of this that I gave like at SF Blockchain Week maybe, or I think that's online. Or somewhere else, anyway.
Have you given much thought to support for layer 2 protocols?
To be honest, we've really been kind of focusing on the core functionality right now. It's something that I think is definitely worthwhile. I think layer 2 protocols give you probably a good constant factor improvement over the base blockchain. So something worth investigating. But yeah, sorry. What's up?
You go over how a smart contract work in this setting. So say you and I implement a smart contract. How exactly would you do it?
Well, okay. The short answer, SNARKs can certify any computation. So.
Right. Is it similar to like the way scripts work in Bitcoin, where I guess you would have to reveal the miner or the
I guess it's hard to say. I mean, there are many conceivable architectures. One could be actually kind of like scriptless scripts in Bitcoin. Sometimes in Zcash, if you go on, if you talk to Zcash people, they will sometimes call this like pay to verification key. That's one way of doing it. There are other ways of doing it. There's like kind of virtual machine approach, which is SNARKs can certify any computation. In particular, they can certify the computation of some virtual machine, and you run that VM inside of a SNARK. It's the same thing.
so you can even have state.
Sorry?
So you can even have state.
Yeah. So right now in Coda, the state is basically the database of accounts, but it could be anything. What's up?
So it would be fair to say that if you implement this in a Proofofwork blockchain, then kind of like an improvement to SPDs.
That's right.
Trust.
Yeah, that's right.
So would you consider merits of different consensus protocols instead of proof of stake? If you kind of new implementations, innovative implementations, fast, etc., reliable, from a computing standpoint, would you consider kind of to do it kind of pluggable, consensus rather than relying on the current one which you kind of
I mean, as I say, if the consensus protocol is based on the wasting of electricity, okay. Yeah, I mean, I guess, I don't think proof of stake is great. I think proof of stake is okay. It still kind of sucks, like, okay, the people with the most money win. I don't know how one feels about that. Certainly, to me, it's better than throwing more coal in the fire, as I said. If there were something better, I'd be very happy to think about using it.
So would it fair to say that when you see reasonably good implementation, reasonably mature implementations of implementation of a consensus protocol, you are ready to switch with proof of stake or something like that?
Well, it's hard to say. I mean, let's get to the mainnet first, and then maybe we can talk about it.
Final question?
Oh yeah, let's do that.
Similarly to the smart contracts question, how feasible would anonymous and shielded transactions be?
That you could totally do. The most straightforward thing that I can think of would be to do like confidential transactions. I don't know, pick your favorite implementation, G to the X or whatever, with range proofs. You could totally do that. I didn't think about Zcash or zero cash or whatever. But I think you could do that too, maybe. That's a little trickier because the state just grows forever, so it's kind of like, but you could still do it. Okay.
All right. Thank you.